Hi, my name is Ronen Shekel. I'm a PhD student in the Bromberg lab in the University, and I will talk to you today about shaping entangled photons through thick scattering media using an advanced wave beacon. Entangled photons have been used in recent years for various quantum technologies, such as quantum key distribution and quantum imaging. However, in many cases, scattering and aberrations are caused due to things such as a turbulent atmosphere or biological tissue, and this scrambles the information encoded in the entangled photons. In this talk, I want to show you how we can use a method from wavefront shaping in order to compensate for this scattering. In wavefront shaping, we consider some light which is propagates through some scattering medium, resulting in a speckle pattern which can be measured using a camera. It has been shown that we can use an SLM, a spatial light modulator, to overcome this. For this, we use some optimization algorithm, which uses feedback from the camera and finds a good phase put in the SLM such that the light will be focused after propagating through the scattering medium. We would like to do something similar for entangled photons. So let me explain what I mean by entangled photons. We generate our entangled photons using spontaneous parametric damped conversion, or SPDC, where some strong pump beam hits a nonlinear crystal, and with some low probability, one of the blue photons will be annihilated, and a pair of entangled red photons will be generated. Since momentum must be conserved, the transverse momentum of the two red photons, or their emission angles, must be anti-correlated. The resulting quantum state is a highly entangled state of a superposition of all the different emission angles where the angles are anti-correlated. To measure these correlations, we place two single photon detectors in the far field. One of them is fixed in place, and the other scans the transverse plane. And we count coincidence events, which are events where both photons are detected simultaneously. As we can see, and as we expect, so we see coincidence events only when the two detectors are placed exactly symmetrically across the optical axis. And we get this nice focused spot. However, if we now place some scattering medium after the nonlinear crystal, so the correlations are scrambled. Instead of the tight focus, we get this two-photon speckle, which is a speckle in the correlations between the photons. And our goal would be to use wavefront shaping in order to recover the strong correlations. So how do we do this? So the most naive approach would be to do exactly like in classical wavefront shaping, use feedback from the camera. So now we'll use feedback from the coincidence rate and do the optimization and find the best phase mask. The problem is that inherently the coincidence counts provide a very low signal, and performing optimization with a low signal is very hard and very noisy. What we would like to do is use some classical feedback mechanism in order to use a strong classical feedback to optimize the quantum signal. This can be done in several ways. The first way is using a beacon beam. We can align an external beacon beam and align it with the optical axis of the SPDC process, send it through the same scattering media, and use it as feedback. This is great since it provides us with a strong signal. But the problem is that co-aligning the laser with the entangled photons might not always be so easy. A second approach that we proposed in recent years is called the pump shaping. And in this approach, we send the classical pump beam stimulating the SPDC process through the same scattering medium and use the pump beam for feedback. In this method, again, we have a strong signal. And this time, the alignment is quite minimal because, by definition, the pump beam is aligned with the entangled photons. The problem with both of these methods, however, is that they optimize only a very narrow range of angles around the optical axis. This angle range is actually defined by the thickness of the diffuser, so both of these methods are good, work well only for thin diffusers. What we would like to propose is a new approach that will both provide a strong signal, require minimal alignment, and work for the most general configuration. And for this, we propose Klyshko optimization. Klyshko optimization is based upon the Klyshko advanced wave picture. And Klyshko, D.N. Klyshko, he considered this two-photon experiment where we have some general linear optics, and at the end we perform the coincidence counts. And he proposed an analogous classical experiment that will give the same result. In this experiment, so one of the single photon detectors is replaced by a laser, and light is emitted from the laser through the general linear optics of the system, and in the crystal plane it is reflected as though by a mirror, propagates again through the optical system, and finally is mirrored using a simple camera that measures the intensity. And what he showed is that the intensity in this Klyshko configuration, in this advanced wave picture, will be the same as the coincidence counts in the quantum experiment. Great, so how do we use this? So we consider the most general setup, where we send the tangled photons and probabilistically send each one of the photons to a different diffuser and perform the coincidence measurements. As expected, since we propagate through diffusers, we will get this 2-photon speckle. Now we take the exact same setup, and the fibers that till now collected the single photons will now be connected to a classical laser and to a power meter. In addition, we of course will add, with some flip mount, a mirror in the crystal plane. Light will be emitted from the laser, will reach the crystal plane, will be reflected, and will finally be measured after propagating through the second diffuser using the same collection fiber from the quantum experiment. Remarkably, the classical speckle pattern we measure is exactly the same as the 2-photon speckle in the quantum experiment. So now we can perform the optimization with the SLM in the classical experiment with a strong signal, and use the same phase mask on the SLM to now localize the quantum correlations. Let's see some results. Before the optimization is done, so we see that both the classical intensity and the quantum correlations are both very strongly scattered. We then perform the optimization on the classical signal, and we get this nice tight focus in the classical signal. Then we take the same phase mask on SLM, and we put it in the quantum experiment, and indeed we see that the quantum correlations are strongly localized, and this is what we wanted to do, so we are very happy. Note that doing the same thing with 2 different diffusers, where each photon propagates through a different diffuser, is not straightforward to do using a regular beacon laser, because one would ask, through which of the diffusers should I send the beacon laser? And really, with our method, our beacon Klyshko beam propagates through both of the diffusers in one simple run. Okay, so I showed you that we optimize, but only on the optical axis. And when you optimize on the optical axis, it also optimizes some small range next to the optical axis. But we want to optimize for all the different angles. But if I go and look at angles further away from the optical axis, the correlations decay and become weaker and weaker. And say now we want to optimize in this region of the angles. Using our method, we simply rerun the Klyshko optimization and regain the strong quantum correlations. And note that there's no need for any realignment, since the Klyshko beam is automatically aligned with the quantum experiment that we want to do. To summarize, we have shown how we can use classical feedback to shape entangled photons through general complex media. We provide a strong signal, we require minimal alignment, and the method works for the most general configuration, both with 2 different diffusers and for thick diffusers. As an outlook, the Klyshko picture guarantees us that the classical and quantum signals will be mathematically the same. In the lab, of course, this is only approximate. This is mainly due to several assumptions of the advanced wave picture. Namely, it assumes infinite phase matching, meaning that the SPDC light is emitted to all angles with equal amplitude, and also a plane wave pump, which allows us to switch the nonlinear crystal with a large mirror. If you want to get even better correspondence between the classical and quantum signal, we can actually implement these experimentally using either a pinhole or some amplitude mask in the far fields to emulate the phase matching, and in the image plane to emulate the pump wave profile. So with that, I would thank you very much for your attention, and I will be happy to take questions. Thank you very much.